lecture and then discussion after the coffee break. And the lecture will be Csaba Csaki post SUSY. Okay? Composite Higgs.
I would like to ask you to put on your masks while I'm taking mine off. Sorry for that, but that's how I prefer it. Okay, very good. So the place where we ended yesterday was the discussion of supersymmetry. And what I promised you is that I will show you another type of approach to naturalness-motivated BSM models, and those will be the so-called composite pseudo-Goldstone boson Higgs models, or also known sometimes as little Higgs models. And they are also related to extra-dimensional, warped extra-dimensional models. I'm not sure if I will be able to get to warped extra dimensions, but hopefully at least I will be able to give you a good overview of what the composite Higgs models are and what their basic predictions are, what to look for there, what the mechanism of those models is. So today I will spend mostly on preparation for actually writing down the model. So it's going to be a little bit similar to supersymmetry, where in the first lecture we sort of understood all the mechanism of supersymmetry, all the underlying formalism, and then in the second lecture I wrote down the model for you, the MSSM, and all the ingredients. So today I'm going to be mainly talking about Goldstone bosons in general, how to write down chiral Lagrangians for Goldstone bosons, and will lead towards the discussion of what is called collective symmetry breaking, which is the essential ingredient for these composite Higgs, little Higgs type models. Okay, so that's the plan for today. Talk about Goldstone bosons. And chiral Lagrangians. And hopefully soon we will get to the idea of collective breaking that may happen at the beginning of the next lecture. Okay, so why do I talk about Goldstone bosons when I talk about composite Higgs? As you will see, once the appropriate point comes, just making the Higgs composite is usually not enough to solve the hierarchy problem. So you will need to add one additional ingredient to that setup, and that will become clear once we go through all of these ideas and then start building the actual models. So the composite Higgs usually is also a Goldstone boson at the same time. Okay, so in order to do that, I will have to talk more about Goldstone's theorem and basically how to write a Lagrangian for a Goldstone boson. Okay, so there's Goldstone's theorem. Which is telling you, of course, that if you have a spontaneously broken global symmetry, you get a massless scalar. For a broken global symmetry. So I assume everybody knows this. Now, what's the intuition for that? Yes, the intuition is that you have some symmetry, yes, some continuous symmetry in a theory that has a non-trivial vacuum. Yes, so the usual thing is writing this Mexican hat type potential, yes. So there is some sort of a minimum here, yes. And as long as the minimum is not at the origin, yes, there will be not just a single minimum, but there's going to be a whole valley, yes, that are connected to each other by these global symmetry transformations. And again, that's not a coincidence. It's saying, look, the theory itself is symmetric. Yeah? So the potential has to have, let's say, this rotational symmetry or whatever you are talking about. But the vacuum breaks it. So what breaks the symmetry is your choice of picking one of these points to be the vacua. yes? But all these other vacua still exist. Yes? They have to exist by construction, by the fact that the theory has this global symmetry. Yes? So then, once you look at this picture, it's very clear, you know, what the Goldstone boson is. Yes? The Goldstone boson is just your motion on the bottom of this potential. Yes? It doesn't cost you any energy. Yes? You know, you move in this potential. Yes? And you are moving on the bottom of the valley. Yes? The potential doesn't change. This is essentially like a flat direction. This direction here, yes, this direction that is sort of connecting the different vacua to each other, yes, that's a direction that doesn't have a potential. So not only is it massless, yes, it's truly a potential-less direction. Yeah, so this is the best way to understand Goldstone's theorem. Yes, you can write nice equations and, you know, but this picture with understanding that, you know, all you do is you are moving along the bottom of the potential. Yes, that's what the Goldstone boson is. Yes, okay, and then you understand that that very clearly. So the valley, again, how do you obtain this valley? Yes, you take your vacuum, whichever you chose, yes, and you act on that vacuum with the broken generator. Yes, so you have some global symmetry. Some of the generators are broken by the choice of your vacuum. Yes, if you try to transform your vacuum by the generator that was broken by your choice of the vacuum, yes, that essentially brings you somewhere along this valley, some other point in this valley. Yes, so that motion is actually what you should be identifying with the Goldstone boson. Okay. So in fact, when you're trying to write down the Lagrangian for the Goldstone boson, this is essentially what you're going to be doing. Yes? You say that, well, I honestly don't really care so much, you know, what happens to the directions orthogonal to the valley. Yes? There will be excitations of the theory there, yes. There will be the so-called, these are called radial excitations. Yes, but I honestly don't care so much about it. Those will be massive particles. Yes. And I'm just trying to formulate a Lagrangian for the motion on the bottom of the valley. Yes. So I will sort of, you know, write an effective theory just for the Goldstone bosons. Yes. And so that will be an effective theory that is valid below some cutoff scale, and we will, you know, be more careful about, you know, defining what that cutoff scale of the theory is. But for now, what you should have in mind is that, you know, you have these radial directions, and those will not be part of your effective theory anymore. So those are being integrated out. So roughly, it's an effective theory below the mass scale of those radial directions. Yes, that's what the so-called, this is, you know, the so-called chiral Lagrangian is. So roughly, and again, you know, we will be more precise about formulating what the cutoff is, but roughly, you know, below the scale of these radial modes, that, again, you know, I don't really care about. And so the beauty of, you know, this formulation, this chiral Lagrangian, will be that it really won't care about, you know, how this global symmetry breaking is happening. There are different ways of doing global symmetry breaking. Yes, you can just write a scalar potential like I did over here. Yes, and think of it as, you know, you have a bunch of scalars, they had some global symmetry, it gets a wave. Or it could be like the example I talked to you about already a little bit before, like in QCD, yes, where there is no scalar, yet there is a global symmetry, which is spontaneously broken. Yes? And I would still like to formulate, what the Lagrangian for the Goldstone bosons of the theory is. And this formulation is, going to be suitable for any ways of obtaining Goldstone bosons. Okay. So this will work irrespective of what the mechanism of symmetry breaking is. Yeah, so it works, both for dynamical breaking when there are no scalars, works when there are scalars, and it doesn't matter. Essentially, the Lagrangian of these Goldstone bosons, once you peel off again, these heavy degrees of freedom, is going to be universal. Okay, and that's the Lagrangian that we are after. Okay, so let's try to see how we should do that. Yeah, so let's assume that I have some global symmetry G. G is the global symmetry, and it's broken to some subgroup H. So this is the unbroken subgroup. And it's broken due to some vacuum expectation value. So let me call this U0 is a vacuum expectation value. Of what? Well, whatever causes the symmetry breaking. Could be the VAV of a scalar, could also be the VAV of a composite object like in QCD. So we will discuss that QCD example in detail. I mentioned already a few days ago that there is this chiral condensate of quarks in QCD. Could be that. Or could just be some scalars that get some expectation value. Yes? And this one is in some representation of your original theory of G. Yes? And what I told you is that in order to get the parametrization of this valley is all I need to do is take my broken generators, yes, and move along those broken, do some transformation with the broken generators on my VAV. Yes, so that's what I'm going to do. So I'm going to define this field, U of x, as doing some transformation along the broken directions. So these are broken directions. These are generators that are broken. Of course, it doesn't really have to be, because the generators that are unbroken, yes, they will annihilate the vacuum. So you could have as well put in all the generators, but the only thing that will be non-vanishing is anyway just the broken parts. Yes? And these are the transformation parameters. Yeah, so this is telling you how much rotation, how much did I move along this valley. And this epsilon, I'm going to promote to be a field. Okay, I'm going to call it pi a over f. Okay. So I will promote this transformation, how much I moved. As we know that these massless directions, they correspond to, transformations in the broken direction. So I just say, okay, let's just do it. Yes, just do the most intuitive thing. Just take that transformation parameter, and that's your field. That's your Goldstone boson. Yes. So I will promote this to a field. Yes. And these pi's will be the Goldstone bosons. As they are usually, Goldstone bosons are often denoted by pi because, the pions of QCD are Goldstone bosons. So that's the That's the traditional way of writing it, okay? So, so very good. So this u of x, again, the u of x, this is called usually the nonlinear field or sigma model field. U of x is e to the I pi a x over f times u0. Okay, so f is some dimensional full scale. It will be related, as you will see, it will be related to the VAV itself. Okay, and the pi over f, again, is literally just the amount of rotation I do, but now, you know, I do a different amount at different points in space, so that's going to be your pion. Okay, so let's try to do this for QCD, yes? We talked about that already, I think, yesterday or in the discussion session. Somebody was asking me about it. So let's do this explicitly for QCD. Yes. And there is a chiral Lagrangian for QCD, and that's what I will try to write down for you in a moment. Well, so we know what the full Lagrangian for QCD is now. Yes, of course, in the 60s, people didn't know what the Lagrangian for QCD was. Yet, Weinberg was able to do what I'm just about to tell you without knowing the actual underlying Lagrangian for QCD. Okay, but you know, it's easier for us to start with, you know, with the hindsight. So you know what the Lagrangian is. You know, you have a bunch of gluons, G A mu nu, some coupling constant minus 1 over 4, whatever normalization, and then you have a bunch of quarks as Q I bar I d slash minus m Q times Qi, yes, and this here is a quark mass matrix. Quark mass matrix. And as I mentioned, in the limit, when the quark, let's say that I have 3 quarks, just to, you know, for simplicity, assume up, down, and strange, like, you know, in the early days in the 60s. Okay, the other quarks are much heavier, so they are not going to play a role in low energy physics. Assume that you have 3 quarks. So in the limit, when the quark masses go to 0, yes, if I set for a moment the quark masses to 0, then this Lagrangian has a large global symmetry. You can separately rotate the left-handed and the right-handed components of the quarks. Okay, and there are 3 of them, so you can rotate the left-handed up, the left-handed down, and the left-handed strange with a full 3×3 matrix into each other, and the same for the right-handed ones. And it's going to be leaving this Lagrangian unchanged. It's going to be a symmetry. So you will have a full SU3 left cross SU3 right global symmetry, and then, as I mentioned, there is also baryon number, of course. And in principle, there is one more U1. It's called the U1 axial. So that's actually the, you know, at the classical level, that's the symmetry, the global symmetry of this Lagrangian. Okay, very good. Now, of course, you know that QCD becomes strongly coupled. It forms a bunch of bound states. Yes. So there is one more SU3 symmetry, which is, of course, the gauge symmetry. Now, that's the one that becomes strongly coupled. These are global symmetries here. Yes? So it's very important that you don't mix up the SU3 of color and these SU3s, which are just global symmetries, which are just corresponding to the fact that I happen to put in 3 sets of quarks. Yes? If I put in 2 sets of quarks, color would still remain SU3, but this symmetry would just be SU2 cross SU2. Okay, so this is just the flavor symmetry, just counting how many different quarks you have put in. And it's essentially saying that as long as the quark masses are 0, there's nothing that distinguishes them. So you can, you know, there is a flavor symmetry, and even worse, yes, because the left and the right don't talk to each other at all. So there's a separate flavor symmetry for the left-handed and the right-handed quarks. Okay. Very good. Now, again, what happens in QCD? QCD is strongly coupled. Yes? So it's going to form bound states. The quarks will not be the degrees of freedom that you actually observe in nature. Yes? It's their bound states, the hadrons that you're going to be observing. But then the question is, what happens to this global symmetry? Yes? In the process when you are forming the bound states. Yes? Well, there are two possibilities. The process of forming the bound states, confinement, could, obey these global symmetries, or maybe it breaks some of it. Okay. So what happens to the global symmetries during confinement? Again, either they are unbroken or they are broken. How do I know it? Well, you have to look at the observed spectrum of bound states, yes, and see, do they fall into multiplets of this global symmetry or not? Yes? If they fall into multiplets of this global symmetry, then that global symmetry was unbroken. Yes? If they don't, then it means that the bound state spectrum doesn't realize that symmetry. Yes? So something must have happened to it on the way down from high energies to low energies, so it's probably broken. Yes? So then, then the question is, what is the global symmetry of the observed hadron spectrum? Yes? Well, so that's, again, what made Gell-Mann famous in the 60s. He said there is an SU3 global symmetry. Yes? And I'm going to call it SU3V. So this is Gell-Mann's SU3 global symmetry. The eightfold way Gell-Mann's SU3. Yes. But very importantly, it's not SU3 cross SU3. Yes. So there is no doubling. So there's no additional doubling of the of all the multiplets. Yes. This would have been called a parity doubling. Yes, because these are left-handed and these are right-handed. So if you had both of them, then sort of there would be a parity doubling of all the multiplets that you observe, and that just wasn't there. Okay. So that means that confinement, whatever the mechanism of the strong interactions is actually going to take this SU3 left cross SU3 right global symmetry and break it spontaneously. Yes?
So if this SU3 left, SU3 right existed, you would see two degenerate multiplets?
Right.
But they don't have to have the same mass, right?
They probably would have the same mass, yes, because there is no difference between the dynamics of the left and what they would have is different parities. Okay. Of course, that's in the limit of no quark masses. Yes. Now, once you add quark masses, then that modifies the masses of the multiplets somewhat. Yes. So, but I think, because it's it's a vector, like probably would have the same. I think they would probably have the same mass, but anyway, the important part is that they will be close to degenerate, but different parities. Okay, so that's something that we don't see. Yes, but we do see one SU3. You can put objects into single SU3. Yes, so that means that the SU3 left cross SU3 right global symmetry, chiral symmetry, is broken to SU3 vector dynamically. Yeah, so QCD does this. It's a property of the QCD vacuum. Okay? It's not a scalar field that you added. You studied the global symmetry, and it's dynamically broken. That's due to the fact that you have these strong interactions. The QCD vacuum must do this breaking. Yes. So the guess is that there will be, in the QCD vacuum, there will be various condensates showing up, which should be, so they are made out of course, the operators of, they will be composite operators of your original theory, and they will, of course, hopefully you know, the actual composite operators themselves are not fermionic. They should have no Lorentz indices because we don't see QCD breaking Lorentz invariance. Yes? All we see is breaking this symmetry here. Yes? So you should prepare all the objects that, you know, possibly could break the symmetry, or, you know, and those are expected to have some vacuum expectation values. So in particular, you know, this quark, this composite quark operator, yes, is the one that has the right properties to break SU3 left cross SU3 right to the diagonal one. Okay, so this would be, I mean, if you write it out explicitly in terms of left-handed and right-handed guys, so this would be Q bar left I, Q right J, yes, plus Hermitian conjugate. Okay, so that would have a VAV that is proportional to delta ij times something of the order of the QCD scale. Yes, so it's you know, without this condensate, you could independently rotate the left-handed quarks and the right-handed quarks, but with this condensate present in the theory, yes, it's only the simultaneous rotation of the left-handed and the right-handed quarks that is going to be a symmetry of the vacuum of the theory, yes. So that's why we say that this is SU3 vector, yes, because you have to simultaneously do the left-handed and the right-handed rotation. That's a symmetry, yes. But if you do it independently, or if you do it sort of, you know, the opposite way, yes, then that's not a symmetry. Okay, so that's the symmetry breaking. Okay. Of course, there are other condensates, you know, like the gluons get condensates, etc. So this operator itself, you know, can get a condensate. That's fine. It doesn't, you know, doesn't break any global symmetry of the theory. So there are more than one condensate in QCD, yes. But this is the most important one because that's the one that gives rise to the global symmetry breaking. Yes. And then again, you know, this is something that we cannot verify from first principles analytically, yes, because it's a property of the strongly interacting theory. Now, the lattice people who are simulating QCD on the lattice, of course, they can calculate these condensates, yes. So they have calculated it, and they can see that it's in fact there. Yes? So it's not, you know, now it's not such a big mystery. Yes, analytically we still don't have, you know, much of control over this, at least in the non-supersymmetric versions of these theories. Now it turns out, since I talked about supersymmetry, one of the uses of supersymmetry is that if you take QCD and make it supersymmetric, then actually supersymmetry often is powerful enough to tell you a bunch of exact results, sort of exactly this kind of results. In the supersymmetric version of the theory, you can often actually go ahead and, you know, say analytically, or, you know, you have the tools to be able to formulate what the right vacuum of a strongly coupled supersymmetric theory is. So that's one of the reasons, you know, besides, you know, just learning a lot of fun things, you know, why supersymmetry is still useful, even if you think that it's getting less and less likely to be the actual BSM theory. Yes. That SU3 axial is? So SU3 axial is the one that will be broken. So that's the broken part of the symmetry. Yes. So again, this is the symmetry of the high energy theory, and this is the symmetry of the bound states. Yes. So SU3 axial is missing. Yes. So that's the broken symmetry. So SU3 axial, even though, you know, I don't like to write it like this because this is not actually a group. Okay, so people have to be careful, you know, anyway. But the combination of the transformations, when these are equal, yes, that's SU3 vector. When they are opposite, yes, you can say SU3 axial, though again, you know, it's not really a group, yes. So that's broken. Okay, so that's the one that is going to be spontaneously broken by this vacuum expectation value. Okay, so if it's broken, you expect there to be Goldstone bosons. So 8 generators, yes. This one had 8 plus 8, 16 generators, and only 8 is realized on the spectrum, so 8 generators are broken. Yeah, so there should be 8 Goldstone bosons in the theory. Okay? Yes?
Why do you say that this is not, doesn't this satisfy the ACTP-SAIFR?
It does not, yes. Right, so these satisfy, yes, so T left with T left commutator is IFABC, T left C, and the same with the right, yes. Now you can check that if you take the combination T left plus T right, yes, and you take those commutators, then it's satisfied. But if you take the minus, yes, because you have 2 minus signs, it actually gives you back the plus. Okay, so it doesn't close. Okay, so that's not a subgroup of the. For U1 it is, yes. For U1, it doesn't matter how you can take linear combinations, and both of them are going to be actual groups. But for non-abelian ones, that's not true. Okay, so but again, but it's not it's not an issue here. Yes, we just say there are 8 generators. They are broken. 8 are unbroken. So you expect to see 8 Goldstone bosons. Okay, and in fact, this is somewhat verified by looking at the spectrum of QCD, because what you find is that, in fact, there are 8 scalars that are quite a bit lighter than all the other bound states. They are not massless, but they are quite a bit lighter than the other bound states. And so those will be the ones that you would like to identify with the Goldstone bosons of QCD. Okay, so there are the pseudo-scalar octet. So pi plus minus and 0, k plus minus, k bar, and eta. And these are lighter than the other bound states, like the proton of QCD. Now, if they are Goldstone bosons, why are they not massless? Well, they are not really true Goldstone bosons in the sense that the way we started out with is by saying that let me take the limit when the quark masses are 0. Yes? And in that limit, I have a symmetry. Well, the quark masses are not exactly 0. Yes? So that gives you an explicit breaking to the symmetry, which will lift. The way you can think of it is that Mexican head potential will be a little bit tilted. Yes, it's essentially symmetric, but it will tilt that Mexican head potential a little bit. And that will give mass to the Goldstone bosons. So these are called pseudo Goldstone bosons in the sense that they would be Goldstone bosons if, in some particular limit, but we are not living quite in that exact limit. But what limit is important for us is that this MQ is much smaller than the scale of QCD. Yeah, so the really important limit is that the masses of the quarks, MQ, are actually much smaller than lambda QCD. Okay? Because that's what it's saying that, the VAV, yes, and all the dynamics happens at the scale of lambda QCD. Yes, so as long as the quark masses are much smaller than that, then it's a good approximation to start out saying that I had a theory that was symmetric, and I added a small perturbation. Now, if the quark masses were much bigger than lambda QCD, yes, then it means that, you know, the explicit breaking is much bigger than, you know, the spontaneous breaking. So you don't really expect to see anything that is resembling still, you know, a Goldstone-like situation. So that's why, you know, you shouldn't think about, oh, what about the top quark? You know, do I have now, you know, it just doesn't make sense to think about that. The top is much heavier than the scale of QCD, so you actually remove that from the spectrum well before, you know, anything about strong interactions actually happens, yes? So you don't want to include that in this discussion, and the same with the bottom. Charm is sort of borderline. Okay, very good. Okay, so now let me then try to write down how the Lagrangian for these Goldstone bosons would look like. Yes. So what I need to do is I need to identify what my U field is for these pions. Yes. So I'm going to call them pions, even though 3 of them are pions and the others are, you know, not pions, but we all call them just pions because that's the easiest way to refer to them. Yes. So what should I do with this field? Yes. How should I identify that field? Well, again, you know, what we said is that the wave that is giving rise to the symmetry breaking is a condensate of a left-handed and a right-handed quark. Yes. So that's an object that would transform both with the left-handed and the right-handed symmetry. Yes. So this would be an object, this Q bar Q composite operator, the one that gets a wave. Yes. This guy, you can think of it as the left-handed quark, and then this one as the right-handed quark. Yes. So the object is something that transforms as a bifundamental, yes, of SU3 left cross SU3 right. So to properly represent the kind of symmetry breaking that is happening in QCD, you have to introduce this object, yes, that transforms from the left with the left-handed symmetries, and from the right with the right-handed symmetries. Okay, and you know I may have mixed up, you know, which one is the bar. Doesn't matter. Yes, it's like a bifundamental. Yes, and this bifundamental gets a wave. Yes. Because that's exactly the symmetry breaking pattern of QCD. This object, this composite operator that transforms from, you know, both with the left and the right-handed symmetry gets a wave that is proportional to the unit matrix. Okay, so the U has a wave. Let's say that some U0 times the unit matrix. Or let's see. Let me call it like this. Let me call this F times 1, 1, 1, and let me call this U0. Okay. And this is the object that I would like to then promote to be a field which is now going to contain the Goldstone bosons. Yes? So what I want to do is I want to take this vacuum, yes, and start transforming it under the symmetries. Yes? Well, clearly, if I transform it under the vector-like combination, yes, nothing happens. Yes? So if I take U left equals U right, yes, the vector-like combination, so that corresponds to a vector-like transformation. Yes? Both the left and the right-handed ones are the same. Yes? If I try to transform this wave under the vector-like symmetry, nothing happens. Yes? Because, well, we better nothing happens because that's how we built up this whole thing. Yes? That this leaves the vector-like symmetries unbroken. Yes? So you can see it explicitly. If I put here U vector, yes, times F times the unit matrix times U vector dagger, yes, these are, you know, these are unitary transformations, so the U dagger is the U inverse, yes, that leaves this unchanged. Good, yes? I mean, that's what we wanted. It's just a sort of a sanity check. Now the question is, what happens if I do sort of the broken transformations? Yes? What happens to U under broken transformations? That's what going to be the definition of my nonlinear sigma model field, of the basic field of this chiral Lagrangian. Yes, what happens there? Well, so now I put here e to the I pi a ta over f. So these are the broken directions. Yes, times 1, 1, 1 f. And now I'm looking at the broken direction, so that means that the left is equal to the right dagger, yes, but it's the right dagger that is showing up. Yes, so that is equal to the left again, e to the I pi a ta over f. Yes, and now you see this is the unit matrix, so it can, come through, and this is just equal to e to the 2I pi a ta over f, and I don't need to even write the unit matrix here, yes, because this is a 3 by 3 matrix multiplied by the unit matrix. It's just exactly this matrix, and you can put here the f. Sometimes people put the f here, and then they write this as a dimension fulfilled. Sometimes they don't even write the f. It doesn't really matter. It's a matter of choice. Okay, so this is the nonlinear parametrization. Yes, this is the basic nonlinear field that you will be using to write down your chiral Lagrangian. And chiral Lagrangian is the jargon for writing the effective Lagrangian for Goldstone bosons. Okay, it comes from this QCD nomenclature where it's the chiral symmetry of QCD that is broken, so they call it the chiral Lagrangian. Okay, and then this stack. So any Goldstone boson Lagrangian usually is called a chiral Lagrangian, or sometimes it's called a nonlinearly realized symmetry. Yes, but we'll see in a moment why it's nonlinearly realized. Okay, so that's going to be the basic building block for writing down the effective theory of the Goldstone bosons. So let's ask the question, how do the Goldstone bosons transform now under the global symmetries, under the original global symmetries of the theory? So how do the pi a's transform? Well, I should know that, yes, because this is my U. I know how U transforms under U left and U right, so I can just ask the question, okay, how does it transform under the unbroken symmetries, and how does it transform under the broken directions, yes? So under the unbroken symmetries, well, so the U goes to UV, UV dagger, yes? So this is equal to e to the I pi a ta over f. You could put the 2 here if you want. If not, you can just absorb it into the definition of f. Yes, it's just, it's just a constant. So this is how it transforms. Yes, UV dagger. Yes, so you can expand this in power series: 1 plus I pi a ta over f plus this thing squared. Yes, so you see that the way it transforms is complete normal linearly realized transformation. Yes, the pions under the unbroken symmetries transform as an octet, as an ordinary octet of the unbroken symmetries of the SU3 vector. So pi a goes to whatever, pi a ta goes to UV pi a ta UV dagger. Okay, not too surprising. Now the surprising part is, if you ask now the question, how do the pions transform under the broken symmetries? Yes. Let's ask that. Well, we know, again, all I need to do is, so I'm going to do ux goes to some transformation in the broken direction. So I'm going to call this UA e to the I pi a t a over f. And then another UA. Yes, now no dagger here. Yes. And I'm just going to say, OK, so this is some transformation that has parameters CA, TA. This is also e to the I CA, TA. So these are just the amount of sort of axial rotations that I'm trying to do on these pions. Yes? And then this is supposed to go over into the transformed pion field. So this is supposed to go over to the e to the I pi a transformed TA over f. Yes? So this is going to tell you how the pion transforms. So you can just do a power series expansion of the fields on both sides. Yes? So what you find is then, well, so you just write this as 1 plus I pi a TA over f plus I pi a TA squared over f squared, etc. Same thing over here. Yes? And now what you find is that if you compare to leading order, yes, what happens to the pion under these transformations, you see that because these transformations come with the same sign, yes, they are actually not going to cancel out even the leading order term. Okay? Even the term without a pion is not going to cancel out. When I take here the expansion with the 1, and the 1 from over here is not going to cancel. So what you find is that the leading expression is that the transformed pion, TA, is the original pion plus f times CATA plus higher order terms in the pion, order pi squared terms. So under the broken generators, the pion is going to be shifted. Yes? It's going to be shifted by the amount of this broken symmetry that I'm doing. Is it shocking? No. I mean, the pion was supposed to be the the transformation parameter in the broken direction. Now I'm going to do a transformation in the broken direction to leading order. It just shifted the pion by the amount of the broken transformation that I did. So this is the famous shift symmetry. Yes? So you probably heard many times that, pions have shift symmetries, and the shift symmetry invariance implies this and that. It's very simple. That's what it is. Okay? So the pions, the Goldstone bosons, have a shift symmetry. To leading order, yes. It's not quite, there are order pi squared terms, order pi to the 4, there will be higher order terms. If it's an exact U1, if it wasn't non-abelian, then it would be an exact shift symmetry. But in non-abelian theories, there are order pi squared corrections here, so you have to be careful when, so there's a pi a goes to pi a plus CA plus order pi squared, yes, shift symmetry. Okay. Yes. Because this is the broken direction, yes? So the U in general transforms U left, U right dagger. That's the general transformation. Now, in the unbroken case, left equals right. That's the vector like, yes? So then I take, so left equals right, yes? So that means now I'm going to call that vector U, V dagger, yes? Now, the broken direction is when U left equals U right dagger. That's the broken direction, yes? Because that's the one that doesn't leave this valve unchanged, yes? So U left equals U right dagger. So essentially, you put the same matrix to the left and to the right without a dagger. Yes. Okay, very good. So the pion has a shift symmetry, and this, you could say, this is another proof, maybe the most sophisticated proof of Goldstone's theorem, yes? Because clearly, you know, if you had a mass or a potential for the Goldstone bosons, those would not be shift symmetric. Yes, you know, so that also forbids the contribution, so it can only have derivative interactions, no mass or any potential. Okay, very good. So, so now, how do I write the Lagrangian for the Goldstone bosons? Yes, so now it's clear, yes? Well, I have this field. It's parameterized in terms of the Goldstone bosons. And just start writing down all the possible invariants that you can make out of this field, this U field. Yes. So this one should still be invariant under both under the full original symmetry, under U left and U right. Yes. And the fact that the symmetry was broken is captured by the way I am parameterizing that field. Yes. So just take the U and write down all possible invariants. Yes. And you would do this usually. You would organize these operators in terms of the number of derivatives. Okay, so just write all invariants made out of U. Okay, and again, what we think of this is that this is a low energy effective theory. Again, that's how we started, that we are going to try to look at the theory below the scale of these radial degrees of freedom. So we only look at low energies. So we usually organize this in terms of the number of derivatives. Because the more derivatives I have, the more momentum or energy insertions I'm going to get in a particular operator. So in the limit, when I go to very low energies, those operators will be less and less important. Okay, so the terms with the smallest number of derivatives will be the most important, and then there will be corrections corresponding to terms with increasingly higher number of derivatives. Now, of course, once I reach that's true at low energies. Once I reach the limit of this theory, once I reach the cutoff of this theory, then those terms with the higher and higher number of derivatives will start becoming equally important. Yes, and the theory doesn't, you know, is not going to be very predictive. But at low energies, in the limit when you know, the energy goes to zero, then this will be a very nice and predictive theory. So so what are these operators? Yes. Well, first, let's say no derivatives. So I want to make an invariant out of U, yes, that contains no derivatives and is invariant under SU3 left cross SU3 right. Yes. So I can take U dagger U. Yes. So now that's invariant under SU3 right, and I can take the trace of that. Yes. And that is going to be now invariant under SU3 left cross SU3 right. So this could be a term in the Lagrangian, except, well, U dagger U is 1. So it's a very trivial invariant. Yes, it doesn't depend on the Goldstone boson field. So, you know, even if you try to add it, it doesn't give you any non-trivial theory. Okay, so and there's no other invariant that you can make out of U dagger U without derivatives. Now, with two derivatives, what you can do is you can take d mu U dagger d mu U and take the trace of this. Yes. And Well, first of all, why is this invariant? Yes. So this should be invariant under global SU3 left cross SU3 right transformations. Yes. So that means that whether or not I have this derivative here doesn't matter from the point of view of finding what the invariant is. Yes. So the invariant essentially is still U dagger U. Yes. But now because I added these derivatives, this is not going to be trivial in terms of the Goldstone boson fields anymore. Okay. And then, so it depends on whether you put the F already into the definition of U or not. So you see you have two derivatives. You want to make something that is dimension 4. Yes. If you didn't put the definition, if U is just, if your definition is that U is e to the I pi a t a over f, yes, then people usually put another f squared here. Yes, and in fact they put f squared over 4. What fixes this over a coefficient? Well, the fact that I want to leading order, I want to get a canonically normalized kinetic term for the pions. Yes, so I start expanding this exponential. There's a derivative on it. Yes, so that will give me a d mu pi a, yes, divided by f. So in order to get canonically normalized pion fields, yes, I need to multiply this by f squared. Yes?
Why are we looking for invariance under the unbroken?
I'm sorry?
Why are we looking for invariance now under the unbroken?
I'm not just under the unbroken. I'm looking at invariance under the full original global symmetry. Yes?
We're looking at the low energy.
But again, you know, so the fact that the symmetry is broken is taken into account how I'm parametrizing the field, yes? But I'm still trying to write a theory that has no explicit breaking, yes? If I wrote something that is not invariant under the left and the right symmetries separately, yes, then I would write an explicit breaking. Okay, so the effect of the spontaneous breaking is captured in having the nonlinear parametrization of the field. Yes, but once I did that, I better write. I mean, the Lagrangian, you know, shouldn't break the symmetry explicitly. Okay, so all the terms in the Lagrangian, they are actually invariant under the full thing, left cross right, not just the unbroken symmetry. Yes. And the point where the breaking comes in is that, well, this field here doesn't contain a full multiplet, yes, of SU3 left. In fact, it contains only a pion, yes, that is sort of, you know, a weird mixture of, you know, things that transform, you know, linearly under the unbroken, non-linearly under the broken symmetries. So that's the way this construction works. All right, very good. So now, this one here actually is going to give you the interactions of the pions. Yes? So this will be something non-trivial here. Okay, so you can start now expanding, you know, this U field in terms of the pions, e to the minus I pi a t a over f. d mu e to the I pi a t a over f. Yes, so you can start expanding it. Yes, and you will get, of course, the kinetic terms. You will get terms like pi a d mu pi a squared. And then you will get terms of the form d mu pi times pi squared. Yes, divided by 1 over f squared. And then you can calculate what the coefficient of these terms are. Yes, so you will get these terms that are actually describing the scattering of pions with each other at low energies. And then, you know, higher order terms, there will be terms with 6 pions that will describe, you know, 6 pion scattering. But this is the most important one. Yes, this is the one that is telling you if pions scatter at low energies, you know, it will tell you what the coefficient is. And at this point, you know, there's nothing unfixed. So this is an actual prediction, yes, that is completely fixed by the symmetry breaking pattern of the theory. Okay. Of course, there will be corrections because you can add then terms with, you know, more derivatives, etc., but they will be suppressed. So this will give you the leading term for the pion-pion scattering at low energies. Okay. Very good. Now, where are the electroweak interactions? Where are the electroweak interactions? Well, actually, the electroweak interactions, SU2 left cross U1 hypercharge. So they are actually embedded into the global symmetries of QCD. So they are a subgroup of SU3 left cross SU3 right cross U1B. Okay? And it's got to be like that, yes, because QCD is part of the standard model. The SU2 cross U1 is an exact gauge symmetry, so it better be part of the global symmetries of QCD. Otherwise, it couldn't, you couldn't have a reasonable theory. Yes, and the best way to understand it is that the SU2 left is actually living up here. SU2 left is actually living up here, a subgroup of SU3 left. Okay, it's a little bit of a cheating, yes, because the strange and the charm, they also form a doublet, and this is a theory where the charm has been already integrated out. So if you want to be a little more careful, you can do it. I'm not going to try to deal with that. Just for simplicity, we'll just assume that it's embedded as the SU2 subgroup of SU3 left. Yes. So then, like I told you already before, yes, this is SU2 left is a subgroup of SU3 left, but SU3 left is spontaneously broken by the QCD vacuum. Yes, so that means that my SU2 left, the actual SU2 of the weak interactions, is spontaneously broken by QCD. Okay, so the same VAV, this Q bar Q VAV, this Q bar Q condensate, is breaking the SU2 electroweak interactions. And this chiral Lagrangian can actually tell you how. Yes, because what I can do is, once I know that I have embedded it into the SU2 subgroup of SU3, yes, then I can take now my chiral Lagrangian and promote these derivatives to be covariant derivatives. Yes. So my covariant derivative acting on this chiral, on this nonlinearly realized, chiral field, yes, will be the ordinary derivative minus Ig times W mu A 1/2 tau A Ik. So this is here, there's a Uij, and then there's a Ukj. Yes, so basically, the first index transforms under SU3 left. Yes, and the SU3 left contains the SU2 left. So I just gauge it. So I just, I know how it transforms under SU3 left. A subgroup of that is gauged. So I'm just going to shove it in, yes? And then actually, you can show that the B, the U1 hypercharge, that's actually the diagonal subgroup of the right-handed interaction, of the right-handed SU3. Okay, so there will be a plus Ig prime B mu times 1/2 tau 3 R, okay, Kj, and now this one is acting on the second index, on the index corresponding to the right-handed symmetries. Okay, that's it. So this is now how you should extend your chiral Lagrangian if you want to include into the chiral Lagrangian the effect of the electroweak symmetries. So this will tell you, for example, how the pion interacts with the W. Yes, so if you were ever worried about, what those vertices are, yes, well, here it is.
So in this, only the first two
I'm sorry? This is SU3 left. Yes, and this is SU3 right. The first index is the left-handed. The second index is the right-handed. So the SU2 electroweak is embedded into SU3 left. Yes. So it acts only on the first index because this was the SU3 left index. Yes. And then hypercharge is actually embedded into SU3 right. Okay, as the whatever, the 1 minus 1 0 as this generator. Okay, so that's why, this one here is acting on the second index. Okay. And now, of course, if I now write down, the modified version of this chiral Lagrangian, well, guess what? You're going to get mass for the W and the Z. Yes. Because those symmetries that have been gauged by the W and the Z and the Z, they are actually spontaneously broken in the QCD vacuum, yes, and this chiral Lagrangian captures that. Okay, so if you now start writing down d mu u dagger d mu u, the trace of this with f squared over 4, yes, now you see there will be, a W here, another W over there, and then there will be a term where I just take the unit matrix, yes, and that's going to give you a W mass. Okay? So there will be a term in this that is just going to be G squared F squared over 4 times W mu plus W mu minus plus G squared plus G prime squared over 4 F squared times 1/2 Z mu Z mu. Okay? Not only does it give a mass to the W and the Z, it actually gives exactly the right mass, the right ratio of masses for the W and the Z. Of course, it doesn't give you the right overall mass, yes, because it's proportional to this F. F is related to lambda QCD, yes, so this is less than a GeV mass. Okay, but the ratio comes out beautifully the correct one because that only depends on the symmetry breaking pattern. Okay, and the symmetry breaking pattern here is, if you remember, I haven't talked about this, but somebody was asking about custodial symmetry. Yes, the way the symmetry breaking happens in the standard model is that SU2 left cross SU2 right, where SU2 right is a custodial symmetry of the Higgs sector itself, is broken to SU2 diagonal. Well, guess what? It's exactly this, yes? There's an SU2 left cross SU2 right broken to the diagonal. Same symmetry breaking pattern. So not too surprising that you get the same kind of mass ratios as you get in the standard model, except, again, you are not getting the right overall magnitude. Okay, very good. So that's very nice, very beautiful. Now, let's do one more important thing. How about the explicit breaking? So I told you that I have this chiral symmetry in the limit when the quark masses go to 0, but the quark masses are not 0. Yes, the quark masses are, so there is a term of the form Q bar, M up, M down, M strange times Q in the Lagrangian. So now what I would like to understand is how to incorporate the effect of these quark masses into my chiral Lagrangian. Okay, so here comes again our keyword, the one that I started mentioning already yesterday when we were talking about supersymmetry breaking, that I'm going to do something that is called the Spurion analysis. Okay. So I have this quark mass matrix here. I'm going to call this capital M. Yes. And it's a bunch of numbers. Yes. It's something that the lattice people can maybe calculate. For us, they are just a bunch of numbers that are whatever, you know. They are small. They are 3 MeV, 6 MeV, things like that. Okay, so this is breaking the symmetry explicitly. Okay, so then the question is, how should I try to incorporate the effect of this breaking into my chiral Lagrangian? Okay, so here comes the trick, which is the Spurion trick. That's what smart people like Seiberg or others, I don't know who first came up with this idea. Probably it was already known, you know, for in the 60s when they were talking about doing this. Yes. He said, okay, so let me first pretend that this M is not just a bunch of numbers. Let's pretend that it's actually a field itself. Okay. And it's not just an arbitrary field. It's such that this term would maintain the original symmetries of the theory. Yeah? So this transforms under SU3 left cross SU3 right as a bifundamental, yes, because it's essentially, it's the mass term, yes. So if the mass transforms sort of in the opposite way as a bifundamental, yes, like a anti-fundamental fundamental instead of a fundamental anti-fundamental, you know, then this term would not break the symmetry. Yes? It wouldn't break the symmetry at all. Yes? Pretend that M is a field and it transforms in the right way, and we understand what right way means, that, you know, it itself is a bifundamental, yes, such that when I contract it with Q bar and Q, then, you know, this is a symmetric term. Okay? So then, of course, you know, this symmetry wouldn't be broken at all, but instead, I would have another object, this new field, yes, that I could add to my chiral Lagrangian. Okay? So what you do then in the Spurion analysis is you promote basically the explicit symmetry breaking parameters to fields, assign the quantum numbers to them that is needed in order for the explicit breaking term to not be an explicit breaking term, but to restore the symmetry of the theory, yes? And then use that object, that M, that field, in your chiral Lagrangian. And so now, if I have my M, I could add another term in my chiral Lagrangian. Yes, because U is a bifundamental, M is a bifundamental. Yes, so things like trace U times M dagger plus Hermitian conjugate. Yes. Now, this would be an invariant if M was a field. Okay, I could add this term into my chiral Lagrangian. Okay, so let's look at this modified theory where, you know, these are not mass terms, but it's a field. And now let's say that there's some sort of a potential or something that is forcing the M to actually get a VAV. Yes? So M is a field, but then I give it a very large mass. I could do that without breaking the symmetry. Yes? I could make it get a VAV also without breaking the symmetry explicitly. So let's just do that on both sides of the theory. Yes? And then the effect will be just that on my chiral Lagrangian side, I will have to freeze this field back to its vacuum expectation value. Okay? So now imagine that this field M has a VAV, which is M up, M down, M strange, and it also has a very large mass. So essentially it doesn't play a role in your chiral Lagrangian, except that this term is now allowed, yes, which is an additional term that, once I freeze the valve to have, this particular structure of the masses, then it's going to be, it's going to give you the effect of these masses on the chiral Lagrangian. And of course, eventually, you won't go through all of this, promote it to a field, freeze it, etc. At some point, you get so used to it, you just say, okay, M is a spurion, it transforms as a bifundamental. I can write this additional term in the chiral Lagrangian. Yes? So that's how, in practice, you do it. Yes? But what is always behind it is that, well, I could have considered a slightly different theory, which at low energies is indistinguishable from the one that I'm looking for, yes? But in that case, this explicit breaking would not be an explicit breaking, but would be a spontaneous breaking. Okay? And then once it's a spontaneous breaking, then you can follow through, the effects of that in your effective Lagrangian, and this will tell you how this mass term can come into the what the effects of the explicit breaking are on your Lagrangian. Okay, so this is the essence of Spurion analysis. Okay, and that was sort of the same story. I didn't say it in this much detail yesterday about supersymmetry breaking. Yes, that SUSY is broken, but I pretend that it's actually a web of that field S, and then I try to write down all possible terms in the Lagrangian with S, and then see, okay, which SUSY breaking terms do I get? Yes, that's essentially what we did yesterday. Okay, very good. So now, once I have this Lagrangian, once I have this additional piece in the Lagrangian, you see that I can start expanding, my pion 1 plus I pi a T a over F plus, this thing squared, yes, pi a T a squared, etc., times M. Yes, and the M is M up, M down, M strange. Yes, I have the trace of this. And plus Hermitian conjugate. So you see the term that is linear in the pi drops out from the Hermitian conjugate. Yes, and you are going to now explicitly get a mass term for the pions that are proportional to the quark masses. Okay, and not only do you get some mass term, but you get a very well-defined relation between the masses of the various pions and the different quark masses. So you get some corrections to the pion masses. M pi squared, this is proportional to mq over f squared. Yes. The quark masses, pion, this f squared, the pion web, or whatever QCD web squared. And then, there's some overall coefficient here that you didn't know what to add. And that's just going to be there, I guess, to make this a mass squared term, so some mu squared here or whatever. Sorry, mu cubed. Something of order lambda QCD probably, but. And so this gives you the shifts in the pion masses and also gives you particular relations, yes, because, M up, M down, and M strange are not quite equal, yes, they are known quantities now, and they will give you some relations among the various pion masses. Okay, so in particular, the famous Gell-Mann-Okubo mass formula is exactly showing up like that. So if M up, if you assume that M up is of the order of M down and much smaller than M strange, then you get the mass relation that M eta squared plus M pi squared is equal to 4 mk squared. Okay, so that's just, again, just take this matrix. I guess I'm going to give this as a homework. Let's just take this matrix, write it out, multiply it out, and make the assumption that these two elements are equal, and then you will get this famous Gell-Mann-Okubo mass formula. Okay, so very good. So you understand now how to include the effects of explicit breaking. Now, this is not the only explicit breaking. Actually, there's one more, and I guess I'll put that also in the homework, which is gauging QED. So including the effect of the electromagnetic interactions. That's also an explicit breaking, because you take some of the global symmetries, a subgroup of the global symmetries, and you gauge only a subgroup and not the entire thing. That tells you that actually some of the generators within the symmetries was treated differently than the others. So that's an explicit breaking. And that will actually give rise to other corrections, SU3 breaking corrections to your pion Lagrangian. In particular, the pi plus minus and pi zero mass difference is arising from that. So that's another nice exercise that you can do. Try to sort of see what is the right spurion for QED. Yes, it will be related, of course, to some sort of a charge matrix. Yes, it's the charges of the quarks that are going to be responsible for the explicit breaking. Sort of think about promoting those to spurions and then see how you can use them in the chiral Lagrangian. Okay. Now I would like to do one more thing today before letting you go, and that's the last thing that is sort of needed in order to set up for tomorrow the actual construction of these little Higgs models or composite Higgs models, which is to find out what the cutoff is for these chiral Lagrangians and how to do what is called a naive dimensional analysis for these chiral Lagrangians. So it goes under the name of NDA. Again, it stands for naive dimensional analysis. Okay. And it's basically asking the question that this chiral Lagrangian clearly is non-renormalizable. Yes. I have put in fields into the exponentials. Yes. I'm going to have arbitrary powers of the pion fields showing up in this Lagrangian. Clearly, this theory is non-renormalizable. You should not be thinking of it as a fundamental theory. You should be thinking of it as an effective theory below a cutoff. Yes? And we sort of understand the origin of the cutoff. As I told you, it's essentially, you integrated out those radial degrees of freedom when I started with the Mexican head potential. Yes? But I would like to now see, okay, if I have one of these chiral Lagrangians, how can I just, by looking at the chiral Lagrangian, determine where the cutoff of the theory is? Okay, so where is the cutoff of the theory? Okay, well, so let's look at our pion Lagrangian. Yes, what I said is that it will have a non-trivial interaction vertex. Yes, that will be the first non-trivial term coming from this d mu u dagger d mu u. Yes, it will have two derivatives. So it will have v pi squared and then two more pions and then 1 over f squared. Yes, and some numerical coefficient, again, something that you can calculate, but it's not very important for us. So how will this vertex look like? Yes, so this has 4 pions. Yes, it has a 1 over f squared in it. Yes, and then it has 2 momenta. Yeah, so it's something like p squared over f squared, where p is some momenta of the external pions. Now, how should I find the cutoff of this theory? Yes? Well, what I can do is I can ask, let me take this vertex, yes, and calculate a loop diagram that includes these vertices. And my requirement for the cutoff will be such that the contribution that I'm generating should be subleading at least smaller than what I get from the 3-level effect. Okay, so the requirement, that's what NDA is essentially requiring for you, is that the effects of loops should be smaller than the 3-level effects. Ideally, they should be much smaller, yes? But at least they shouldn't be bigger, yes? So with this, I'm going to estimate a cutoff for you. And what that estimate will tell you is that the cutoff better comes in a little earlier than that, yes? This is the very last point where the cutoff could show up, yes, in order for the theory to really still be predictive. Okay, so what I can do is I can take two of these vertices, yes, and close them up. Sort of, you see, I don't know if it's nicely visible. Yes, I'm going to trace it here. So I have two of these pions, yes, and close it up like that. Yes, and I'm going to try to compare the result of this calculation with the original vertex from here. Okay, so how large is this? Well, it has one loop. Okay, so it has a loop momentum d4k. It has two propagators. So it goes like 1 over k squared squared. It has two of these interaction vertices. Yeah, so it has a 1 over f squared squared, so 1 over f to the 4th. One loop factor always gives you 1 over 16 pi squared. Okay, and the vertices, yes, they also come with momenta. There are two of them. Yeah, so in principle, you should put k squared squared, yes, but I'm trying to compare it, the effect, to a diagram that already has some external momentum, so I need to make two of these momenta to be external momenta. Okay, so the contribution of this diagram that is to the same operator as the one I have at tree level, yes, would be estimated like this. Okay, so now you can see that this is of the order of, so there's p squared, 16 pi squared f to the 4, yes, and now this integral here, yes, there's d4k over k squared, yes, so this will be quadratically divergent, and so that's where the cutoff is going to come in. So it's going to be, there may be a numerical factor, but the expectation is that it's something of the order of lambda squared, and that's what MD8 tells you to do, just ignore all the numerical factors, just count these loop factors, count the powers of divergences, and then that is going to give you an estimate for the divergences, yes? And now I would like to compare this with this expression here, yes? And I would like to impose that this is smaller than p squared over f squared, yes? So I will peel off one factor of p squared over f squared, so that tells me that lambda squared over 16 pi squared f squared should be less than 1. Okay, so that tells me that the cutoff so lambda should be less than 4 pi f. Okay. So you probably hear many times when people give talks that lambda is 4 pi f, yes? This is where it is coming from. This is the essence of that estimate. So this is where the cutoff should be, or earlier, yes? So lambda equals 4 pi f is the latest. And in fact, you can show that if your theory is strongly coupled, so if your couplings are of the order of 4 pi, yes, then that's where the cutoff is going to be. If your theory is not so strongly coupled, for example, it came from a weakly coupled Higgs theory, if g squared is g star is less than 4 pi, then the cutoff usually comes in at g star f, okay, where our new particles are going to be coming in at this scale. Okay, almost done. Sorry, let me just say one more thing. So this is how you estimate the cutoff of the theory, and then you can actually do really a naive dimension analysis for estimating the terms in the Lagrangian. So terms in the Lagrangian, how will they look like? Well, so every Goldstone boson always comes with pi over f. So each Goldstone has a 1 over f, yes? It comes from the fact that it always came from pi over f, yes? And the remaining dimensions are made up by, this cutoff or, whatever the scale is. So the remaining dimensions made up by lambda, or, if your theory is not that strongly coupled, it could be made up by G star f. Okay, so for example, if you want to have a quartic, how large will a quartic be in a theory like this? Well, okay, let me not do this now. Quartic turns out to be, for example, G star squared. Okay, so you can go through all of these rules and then estimate, okay, if I now have some sort of a term that is generated for my Goldstone bosons, how large are they going to be? For a quartic, you're going to get something of the order of G star squared. Okay, very good. So let me stop here. Just a little preview. So now we have all the technical tools that are necessary. And so tomorrow we'll start out with actually building a theory where the Higgses are Goldstone bosons. And we will end up at least with the simplest version of these composite pseudo-Goldstone boson Higgs models or little Higgs type models. And we'll see, how the cancellation of the quadratic divergences happens there, what the flavor structure of those theories are, and what kind of experimental consequences those theories would actually have. All right, let's stop here.
So, okay, there's a question over there. Maybe a quick couple of questions. Go ahead. So that we can have our 15-minute break and then back to the discussion. So some of the questions, if are longer discussions, we can do later.
Yeah, I'll come back, so I'll be here.
So in this naive dimensional analysis, I see that you probably omit the explicit breaking, right? Because pions are massless.
Right, yeah.
So what effect does this induce? And in particular, would you have some kind of like regulator for the divergence from the mass?
So, I mean, so the explicit breakings, of course, you're going to include, yes, but so those you will include as an additional parameter, like I defined over there, with the same rules, but then there's just another object, essentially, could be dimensionful or dimensionless, depends on what exactly the nature of that breaking is. Usually, it's better be dimension full, yes, because those are the ones that don't introduce very divergent contributions. So, you can just take that M and, use that, with the same rules for dimension analysis, yes, to get a term in the Lagrangian. And what was the other question? Sorry.
So I'm not sure, but I think maybe if you put mass in the propagator,
does
it regulate?
You're asking about the regulator, yes?
Yes.
Well, I mean, it's a theory with a cutoff, so you don't need to regulate, yes? It's by definition finite, yes? It has a cutoff, so there are no UV divergences because, say, the theory is not even valid there. Don't even try to go there, yes?
Okay, thank you.
Yes. So,
Super briefly, can you repeat how is the link between the cutoff scale, the limit of the theory, and the strong coupling? So the G star F.
right. So again, so this is the highest. This is the highest the cutoff could be, yes. And it turns out that when the coupling is of the order of 4 pi, yes, then this 4 pi is actually originating in the fact that the couplings are large, yes. Now, if the theory is not that strongly coupled, yes. So, for example, in QCD, essentially the coupling is not quite 4 pi, but it's close. I think it's more like 2 pi. Yeah? So what I'm trying to say is that, where exactly the cutoff shows up is going to be related to how strongly and by cutoff I mean the new particles. Yes, the new particles that you have sort of integrated out, yeah? So the radial modes. And so if you have a Higgs-like theory here, yes, the coupling is not, is not that big, yes. Well, the expectation is that it's going to be, wherever the VAV is, yes, times a coupling constant. That's essentially the going to be the scale of the new particles.
But because the dynamical chiral symmetry breaking scale is related to the size of the coupling,
right?
Always,
Yeah.
right?
So well.
But is there a diagrammatic, like the four Fermi interaction? I don't know. I mean, I wonder if it comes from that line.
Well, I mean, when things are strongly coupled, yes, you don't have anything diagrammatic, yes, because they don't really make sense. But here, when they are weakly coupled, you can just estimate how large the, the masses of these radial modes are going to be, yes. I mean, this is essentially the Higgs direction, yes. So they will be of the order of the VAV times, whatever whatever the coupling of the theory is, yes. It's like, lambda V or whatever it is in the for the Higgs, yes. So.
2PF is one period that the Goldstone boson come around of the vacuum potential, right? And
right.
if the gamma, the scale is less than two periodic decay, because the F is the constant decay, right?
F is the decay constant. It's usually called the pion decay constant.
This broken symmetry, I'm thinking about the Goldstone boson cannot make two period circle around the vacuum in the potential that it was broken.
No, I wouldn't say that there is anything like that. I mean,
no, because I read in your material that was 2PF is the
right.
It was a periodic circle around the vacuum in the potential. Sure. So I think if the scale of to be break is less than 2.
But again, I mean, the motion on the bottom doesn't really cost you energy, yes. So I wouldn't really say that that's related to the cutoff of the theory.
Because I understand if the Goldstone boson cannot make two completely.
But again, I would not, because going on the bottom of the valley, yes, that doesn't cost you energy. So I would not. I wouldn't try to mix up these concepts.
Because the F is decay, so I think.
Yeah, I don't think that's the right way.
It's more like a coincidence,
yes,
trying to read too much. You can go infinitely many times.
I would think so. You can bind around
infinitely many times, and it's zero energy cost.
Okay.
Right.
So, thank you.
You're welcome.
Maybe we should stop for coffee and then come
we'll
back
be
to the
back
discussion.
in a few minutes anyways.
Get your best questions for later.
All right. Good. Yes.
Oh, yes. 2πf. I never thought about
this
period.
Right. I mean, it is a period, but it's just a different, conceptually a different thing.